All right, how is everybody doing on this Physics Friday? It is Physics Friday, right? Physics Friday, Thursday? Something kind of like that? Yeah. Yeah. Where is everybody today? What happened? Strange. Just like a week ago, people were clamoring at the door trying to find a spot. Huh. It's curious. Yeah? It's disappointing. Now I'm sad. I don't know if I can do this now. Look at all these people missing over there, like a whole slew. Yeah. We should, shouldn't we? Yeah. We should have like extra class because they're not here, like to punish them. Or does that punish you all? I'm not sure which.
And you.
And me? Yeah.
Because you have to be there too.
Yeah, it punishes all of us. We can't do that.
Yeah.
I like that. I should teach things today that all of us agree to never share with them. And then it is a question on the first exam. Yes. That's pretty good. Yeah. Like the answer for 30% of the test is B. The last third of the test is B. And now you know that. No. That'd be pretty fantastic, though. Boy, that'd make grading easy on that part of the exam. I couldn't complain too much about that. You know, I'd like to.
Well, you really don't have to.
But I really don't have to.
The answer could just be B for like math questions.
Oh, yeah.
B for math questions. Oh. So they think it's like the answer is like 60, but it's B. Okay. Huh. Things to think about. We should see who shows up on Tuesday and following. Now maybe those of you who are here, you're thinking like, dang it, I was thinking about skipping out. And now you're wondering what might happen. Ah, somebody just got revealed. I saw that. Slamming someone across the aisle. That's wrong. All right, so let's see. Today, I have tried 2 experiments today trying to record the lecture another way and failed both times. Mostly because I ran out of storage on my iPhone both times in 2 other classes, which was depressing. I wanted to record 4K video because I was like, ooh, it'll look fantastic on YouTube, right? And it was like, that's going to be 15 gigabytes, and I didn't have that much room. So I was like, fine, we'll try 1080p. And it's like, still ran out of space. So I'm stuck with the system here, which is 720p, which, you know, it looked okay, but it could look better. You know, you kind of want to be able to see everything that's up there in ultra high definition, but I don't know. We'll have to see. So I'm going to do this for now, and we'll go from there. I'll experiment some more. I'm not guaranteeing, once again, that I'm going to record this every time. People who aren't here, you might not ever get this lecture. Maybe they were thinking, I'll watch it later. Maybe you will, maybe you won't. We'll see. Maybe I'll just leave gaps in the middle. I'll just hit pause every now and then. They just kind of stop. So we were talking about electric potential energy. Electric potential energy. Keep in mind all 3 of those words together mean something different than just electric potential. Notice on the next slide, like the word energy drops off. Don't think that like we're just going to start using shorthand. It's like, forget energy. We know it's energy. These are actually 2 different things. And I hate the fact that 2 very different things have almost the same exact terminology. It's a bit of a problem. So let's go back and first describe again what electric potential energy is, and then I'm going to contrast that with the next slide and what electric potential is. So we've got some equations up here that will tell us how much potential energy a given charge has, and it's all dependent on where that charge is located inside an electric field. Keep in mind, if I take a charge and just put it somewhere where there's not an electric field, it has no potential energy because it has no motivation to move somewhere else. Much like if I take a piece of matter and just put it in deep space somewhere where there's no gravity, well, it has no gravitational potential energy because there's no force that's pulling on it in any given direction, okay? It can't fall. In this particular case, if we put the charge in an electric field, it sort of wants to fall in the direction of the electric field. It feels a force that way. Keep in mind, if I use a negative charge instead, it will feel a force the opposite direction. It sort of wants to fall against the electric field. We say that when there is the possibility for that charge to move, to feel a force and go somewhere else, it has electric potential energy. Much like a mass, if it wants to feel gravity and go somewhere else, has gravitational potential energy. Okay? Do you have the idea of what this potential energy means? Do you have questions? Do you get it? Yes? Yes. Okay? Let me point out something on this diagram over here at the right. I feel like if we keep zooming in far enough, we're going to like see a little creature hiding in here somewhere, you know, like, hi. But, you know, there's nothing there. Just forget that. Okay? Notice these words, potential energy, are pointing to the charge itself. In both cases, and this is important, like they took this line, they drew it literally into the charge, and that was no accident. Because it is the charge that has potential energy. It has a certain amount of energy because it exists in this electric field. Okay? When we talked about masses and gravitational potential energy, it is the piece of mass that has gravitational potential energy because it will fall somewhere. All right? This is different from, next slide, potential. Leaving the word energy off. Let me start by looking at this diagram over here. Notice the arrow here is connected to these words, and it's kind of just pointing to this point right there next to the charge. Again, when they drew these diagrams, this was no accident. The energy is something that the charge possesses. The potential is something about a point in space where there isn't necessarily a charge at all. It's saying that this location right there next to that solid plate has low potential. On the other hand, over here, this little location right here up against this plate is a location that has high potential. All right? If we go back and look at the definition, I literally wrote out, it's like the potential, quotes, of a point in space. How much possibility that location possesses. Okay? Let me explain a little bit more by, well, again, relating it back to gravity. So if we were dealing with gravity, notice they put two different size rocks up at the top. We could assume that those probably have different mass. Well, if they are a certain position off ground, we would say that those two pieces of mass both have gravitational potential energy, but a different amount because they have different amounts of mass. You might remember that gravitational potential energy, we could write that as, if you don't mind, can I just write it as PE? Sometimes U is used, but PE, gravitational, is equal to M times G times H, right? So how much gravitational potential energy a piece of mass has is not just based on where it's located above the ground, but also based on how much mass it has, okay? On the other hand, if I were to just say remove these rocks, yeah, that didn't really remove them, that just colored them, right? And it's like, yeah, I have green rocks now, fantastic. Pretend they're just not even there. How can we do this? I don't know what's happening at this point. They're not there anymore, okay? Those locations where the masses were, they're still in existence there. There's still points in space there that exist this height above the ground. We might say that these locations have potential. They have possibilities. They have options. Because if I put a mass in those locations, those masses will now possess potential energy. It's a subtle difference. Do you hear the way I'm describing those two things? The locations where nothing is located, these locations at height h above the ground, have potential. Literally, they have gravitational potential because if I put a piece of mass there, it will possess potential energy, okay? So in terms of the equations, what we might do is write something like this. boy, I really hate this, but V is what we use for potential. And this is part of the reason why I switched from using U here, because writing a U and a V, trouble, right? So potential energy is MGH. We might say that the potential of those points in space is just G times H. If we were to get rid of the mass, like don't put a piece of mass there, and let's just talk about how much opportunity those points have. Well, they have some potential because there is a height above ground level, and it exists inside of a gravitational acceleration or a gravitational field, all right? So let's relate this back over to electricity and magnetism and all this sort of stuff, and let me make sure I write down the right things. Question?
So V equals GH with no rocks, when the rocks are gone.
If the rocks are gone, those points at that height still have potential. Okay, so we might call this gravitational potential. And this up here is gravitational potential energy. Okay, now over in the electricity side of things, right? Notice we again have this little setup where we can create an electric field in between all these positives and negatives that are on these plates. So there's an electric field that's pointing that way because a positive charge would be pushed from the positive side over toward the negative side. And notice this time they don't have masses. They've decided to put two different charges here, right? One is just charge Q, and one is charge 2Q. Kind of like the masses where I had a mass and then a bigger mass. Now we're dealing with charges. We put them in here, and when they are in this location, we've already learned that they have potential energy, electric potential energy. And we had an equation over on this previous slide, QED, okay? So potential energy, electrical, and I'm going to write this as a magnitude, is equal to Q times E times D. Okay? If I take the charges out, that hasn't changed that region of space. There's still an electric field here, and that point in space is still a point that has a lot of opportunity, a lot of possibility, a lot of potential. Because I know that if I put a charge there, it will possess potential energy because it wants to be pushed this direction. So notice the way these equations are working out. Here I said, okay, remove the mass, and then I can say that this location above the ground inside of gravity has potential. Look at this equation. I can say that if I take out the charge, so let's do that down here, V sub E just equals E times D. These look an awful lot alike, right? Notice there's a certain location, okay? It's a certain distance away from the farthest place it can move to, and it's inside an electric field. Here I had a gravitational field. Here I have an electric field. Those points in space have potential. So the difference is points, where nothing is, has potential. Charges at those points have potential energy. Okay? Can I say that again? Points in space have potential. Charges placed at those particular points will possess potential energy. Okay? So we could go over to this diagram on the left. Not the left, that's the right. Yeah, I've got problems. Apparently it's very much Friday, Thursday. Ugh. We can look at this diagram and like completely get rid of these charges. And we can analyze this setup and say that over on the left-hand side of this region, we could say over on this area, in this region of space, there is high potential, okay? And that amount of potential is going to be less and less and less and less and less as I go across here until I get over on the other side, and we would say that regions of space over here have low potential, okay? The amount of energy a charge has depends on whether I put it into a higher potential area or a lower potential area, okay? Just like, well, the iPad can fall to the floor, right? This region has higher potential than regions right next to the floor. If I put the iPad here, it's going to have higher potential energy. And if I put it in a region of lower potential, it'll have lower potential energy, okay? This is a way, kind of like we did with electric field and force. We went from force, talking about like this charge exerts a force on another charge, and then we sort of like abstracted away from that a little bit and just said that there is an electric field here such that if I put a charge there, it'll feel a force. We're doing almost the exact same thing here, saying this region of space has some properties, it has potential. If I put a charge there, it's going to have energy, okay? These things are all analogous, they all sort of fit together, but they are hard to grasp the first time through. Mostly because this is a lot of stuff that we can't see and touch and play with, and it's just conceptual, okay? I'm hoping in your labs, when you get to play with some of this stuff, that some of it kind of hits home a little bit more, okay? So electric potential energy. Let me see, I have some equations here to give you. Okay, so this one, first of all, the electric potential is equal to the potential energy divided by the charge. And if you think about it, that's essentially what I did when I moved from here down to there. I divided the charge out, and that gave me the potential. We could also write this as U divided by Q if you'd prefer to use that terminology instead. Also, the unit for potential is the volt. The unit for the potential is the volt. And it turns out that it is equal to 1 joule per coulomb. 1 joule per coulomb. And also, beautifully, this is the part you should like. It is a scalar. Yeah, at least one person understands the significance of that being a scalar. Scalar, yay! You don't have to deal with vector addition when you're having multiple things to deal with. So this is supposed to be the easier way to do similar problems. When I'm dealing with energy and potential, it's a scalar. I can just add and subtract things without having to worry about any direction information. So let's switch over to the next slide. A few points I should make. First of all, typically when we're doing problems with potential, we want to focus on a difference in potential between two different points. A difference in potential between two different points. So I could write that something like this. Delta V, a difference in potential, is equal to the potential at point B minus the potential at point A. Or if you wanted to use that equation we had just a moment ago, we could say that this is the potential energy at point B minus the potential energy of point A divided by whatever charge is at those locations. So you see some of these equations starting to fit together now. So since typically we're dealing with a potential difference, if we want to know, like, I don't care how much the difference is between here and here, I want to know the potential at this point, just one of them. The only way for me to get this is to know the potential at one of those 2 points. And there is a way that we commonly do this. We pick a reference point, and this reference point is known as ground, which is perhaps something you've heard of before. When we're dealing with something known as ground, this is a location where the potential, the electrical potential, is equal to 0. So that means if I know the difference in potential, say, between this point and ground is 0, well then the amount of potential at this point is equal to the potential difference. You can see that in this equation, okay? And by the way, ground, we're gonna do circuits and stuff later on. Typically this thing, ground, is literally the ground, meaning Earth. It turns out that the Earth is basically a sort of an infinite reservoir of electrons, of charge, and I can send it a few more charges or I can take a few out of it, and it sort of doesn't care so much. It's negligible to something the size of the Earth. It allows us to have a region of space where there really is no potential, okay? Sometimes also, or we'll say alternatively, we will use R equals infinity, meaning far, far away from any other charges. As a location where V is equal to 0. And I think that sort of makes sense because it's just like with the mass. If I put the mass way out in space somewhere, it doesn't feel any gravity, so it has no potential energy from gravity standpoint. The same idea works with charges as well. And then one more equation. You can see here at the bottom it says the potential difference tells us something about how much energy a charge can gain or lose, or how much work it can do. And we can get back to this idea just by simply rearranging some of our equations. The change in potential energy is equal to Q times the potential difference, or Q times VB minus VA. So reading through this equation, if I have a charge Q, and then there are 2 points where I know the potential. So maybe I know the potential here, and I know the potential here, okay? If I take the charge and it moves from one point to the other, and I know the value of the charge and what the difference is in potential between those 2 points, this will tell me how much its potential energy increases or decreases as it moves between those 2 points, okay? So what are we going to do with all of this? First of all, a slide just with clarification. Notice over on the right, U is electric potential energy, and it is a type of energy which means its unit is joules, just like energies you had before. Other types of potential energy, kinetic energy, all that type of stuff, units of joules. Different from that is this thing that we're calling electric potential. For it, we use V, which is also its unit is in volts. Sometimes we get even a little more lazy with that and just say potential all by itself. So if you hear just the term potential, we're talking about the exact same thing. We're still talking about V, and it's measured in volts. So these two things at the bottom are exactly the same, but they are different than potential energy, okay? So we've got potential and we've got potential energy, two different concepts. Just in case you care a little bit, potential differences that exist kind of throughout the world in different things to give you a feeling for what a volt is and kind of where those things are experienced. A flashlight battery is built such that there is a difference of potential between one end of the battery and the other end of the battery, which is typically maybe about 1.5 volts, give or take a little bit more. You can see as you move up from that, an outlet in your house is typically about 110 volts of potential difference. And keep in mind, potential difference combined with charge starts telling you about how much energy is there, how much potential energy. And of course, as these go up, these are seemingly more energetic, right? Until we get all the way up to the top, thundercloud to ground, which results in lightning. Lightning happens because there's charge that's moving from a very high potential to a very low potential, and you can see the difference in potential there is 10 to the 8th volts, which results in quite the current flow or charge flow from clouds to ground, which is kind of sad, scary, and exciting, and scary. But a little exciting to watch, but scary, okay? So let me ask you a few different questions here related to potential and potential energy. I'll give you a moment to read it, and then we will talk. Hey, things aren't blowing in the breeze today. Should I do this? Did you kind of enjoy that today? The other day is kind of soothing. You're like, please stop, I'm trying to read. I'll stop. I wonder where this phone goes. Can I call anything on this phone? Is that like a phone phone? Or is it like the scary emergency phone that only like dials one number if I pick it up? You should call yourself. See if it works. You might just pick it up and they're like, police. You know, I don't know. Why is there a phone? I don't need a phone. Do you need a phone in here? I don't think so. What's the answer? Any thoughts? 1, 2, 3, 4, or 5. Vote. Vote if you think you know the answer. You're like, we haven't even been reading. We're thinking about this stupid phone. Who says 1? Who says 2? Who says 3? Who says 4? Who says 2? I caught some of you. Who says 5? They feel the same magnitude force, but opposite direction. I would agree with that. Number 3 is meant to trick you just a little bit. But keep in mind, force is equal to, well, Q times E. A proton and an electron have the same Q, and they're in the same E. So they're going to feel the exact same force, but they're going to want to go opposite directions in the electric field. So let's quickly draw that in. The proton is going to be pushed this way, and the electron is going to be pushed that way. So in a way, that's a little bit of a review question from last chapter. What about this one? One, 2, 3, 4, 5, 6, 7. We ran out of questions. I don't know what else. So they experience the same force, but keep in mind an electron and a proton have very different masses, right? A proton is much heavier, which means that the lighter thing is going to have more acceleration. So that would be the electron in this case. Will experience more acceleration. Let's see. So, I hate to do this to all of you. Let me flip through the next 2 or 3 slides. Okay. I can see where we're about to get to today. So we need to connect this back to the last chapter somehow. The last chapter was all about electric fields. It turns out that these things are not separate or distinct. They're sort of like different ways of looking at the exact same problem. Just like there were problems in Physics 220 that you could analyze with forces, and you could maybe look at the exact same problem in terms of potential and kinetic energy, okay? 2 ways of looking at the same thing, but there are connections between them. So any given problem, if there's an electric field that's there are going to be places that have high potential and places that have low potential inside of that electric field. So we have graphed this here real quickly. This is the exact same situation we had before, right? Positive here, negative here, an electric field going this way. We know that on this side we have high potential, because again it's defined on what a positive charge would do, and then the potential goes down as we approach the other side, and you can imagine eventually the charge is going to set against this. Regions of space there have no potential because the charge would have no potential energy remaining. If we were to graph that, and this is meant to line up directly with what you see above, okay? I don't think it does because it's pretty close. I don't know that I copied it perfectly. So this corresponds to this side, and over here we're looking at that plate, okay? We start with some value of potential, and it's as high as it's ever going to be over on this side, and the amount of electric potential I have linearly decreases until I get to 0 over at the other side, okay? In this particular case, we're dealing with a constant electric field, and we can see how the potential varies as we move to different points in the electric field. It's a linear decrease. If I were to write this as an equation, it turns out that the electric field corresponds to the negative slope of the potential, or the negative change in potential with respect to let's write this as L. This is basically a distance or a displacement. Now let's write it as distance since that's what they did at the bottom there. Notice potential versus distance. There's a slope here, a rate of change. That's what this equation is giving us. The negative says it's a negative slope, okay? This tells us how the potential changes in an electric field. Question?
Does the observation that whenever we're trying to observe this kind of scenario where you're using the proton carry over to this as well?
Yeah. All of these equations are set up based on the proton. Everything gets flipped exactly reverse if an electron's in play. Okay, it's all based on what a proton would do. So I can take this equation, and again, keep in mind, it's the negative slope of the potential. The electric field is the negative slope of the potential. And we can rearrange this into an integral. And we're going to do that on the next slide. I'm going to go straight over here. And all I'm going to do is rearrange this and solve for the potential difference instead. It's equal to negative the integral of E dot dl from point A to point B. So we have two relationships that connect the electric field to a potential difference. If you're looking for the potential difference, you can start with the electric field and use this integral to get to it. On the other hand, if you happen to know something about the potential difference, you can use this to solve for the electric field in a given region of space, okay? And we're gonna do an example with this in just a second. In fact, like almost right now, I just wanna point out one thing here. This gives us some alternate units for electric field. Taking a look at this equation, in the numerator I have volts, and in the denominator it's just a distance, so it's meters, okay? Previously the electric field was newtons per coulomb. It can also be volts per meter. So this can also be volts per meter. Either one of those is equally valid. So let me show you a little something about how this works. We're going to go forward 2 slides and we have an example of this relationship between the potential and the electric field. So in this particular case, you can see we have a spherical conductor. So imagine a conductor, we've put some charge on it. All of that charge will be on the outside. We've learned how that works, which means that the electric field will look like this. If I put a positive charge anywhere near it, it's going to be pushed away radially outward. We have learned how to take a situation like this and use Gauss's law to get an equation for the electric field. We learned it looks exactly like what you get for a point charge. So I'm going to go ahead and just write that result down. And again, this comes from Gauss's law in the last chapter. So the electric field, specifically outside this conductor. What's the electric field inside? 0, right? In the conductor will be 0. So the electric field outside is going to be 1 over 4 pi epsilon naught times Q, the total amount of charge that's on the surface, divided by r squared, which is our distance away from the center of the conductor. And you can also write that as kq over r squared if you like that notation better. There have been a few questions about that. K is the exact same thing as 1 over 4 pi epsilon naught. Just depends on which terminology you prefer. You're probably thinking, K. K is easier to remember. It's one thing. Well, true, but there are problems sometimes where having the 4 pi epsilon naught lets you cancel some of it out, and it gets even simpler than K, so either one is perfectly okay. So, okay. Did you catch that? I heard it. I don't know if you did. Either one, K or not K, is okay. I need to go home. That's all there is to it. So delta V is equal to VB minus VA, and we just learned it's equal to negative this integral from A to B, E dot dl. Notice my integral this time, a couple of things. This is a path integral. This dl is a little segment along a certain route that we're going to take. It goes from a point over to another point. It's a path integral, not a surface integral. Also, we have a dot product in there. You might remember the dot product is something like this. It's the magnitude of both times the cosine of the angle between them. It essentially means that we're going to go along a certain direction, and we're only going to use the electric field components that are parallel to that direction, okay? So in this particular case, take a look over on the left-hand side. We are going to integrate from one point outside my conductor over to another point outside the conductor, okay? Essentially right along one of the electric field lines is perfectly fine. So you can imagine that if I'm looking at DL, which is a little piece of the path between point A and B, at all points, it points in the exact same direction as the electric field. So this dot product E to DL cosine theta, well, the cosine theta is just going to be 1, and this is just going to be E times DL, okay? So let's go ahead and simplify that just a little bit. Ooh, let's rewrite this. Oops, that's the pointer thingy. Go away. So this is just going to be minus A to B E dl. Okay? Again, I can make that simplification because E and dl point in the same direction. We have an equation right above for the electric field in this region of space. So I'm going to take it and plug it in. So that means now we have delta V is equal to minus integral from point A to point B, 1 over 4 pi epsilon naught times Q over R squared. And I'm going to change the dl to dr. What's the R direction? Well, it just is along the radius pointing outward. That's the same as the L direction in this particular case. Looking at that, the Q and the 4 pi epsilon naught are all constants. So I can pull those out of the integral. And now I've got minus Q over 4 pi epsilon naught integral A to B 1 over R squared dr. And that's an integral you should be able to do. So let's write that out again. And let's see, that's going to give me something like this, negative 1 over R. And we're going to evaluate that from RA to RB. So point A is distance RA away from the center, point B is distance RB from the center. So let's go to the next step. Let's see, now I've got minus Q over 4 pi epsilon naught. And then inside here, we're going to have minus 1 over RB. Minus a minus, so that'll give me a plus 1 over RA. And then I'm going to pull this negative sign inside here just to simplify a little bit. So that's going to be Q over 4 pi epsilon naught. And then we're going to have 1 over RB minus 1 over RA. Let's take a deep breath and see if you have a question. By the way, here in just a little bit, I'm going to give you a problem to work again so you don't have to listen to me talk for 75 minutes. Because I know it's exhausting. I don't like to hear myself talk for 75 minutes. Does anybody see anything up there that's a little confusing or part of those calculations that don't make sense? We are using a known electric field in our equation to sort of convert it over into a potential difference using this connection between these two concepts. Now, I'm going to make a quick simplification. We are going to let RB go very far away. We're going to let RB go very far away. So we're going to go from a point relatively close, RA, to some point that's very far away from my conductor, okay? Remember, if I get very far away from any charges, then at that point, we could say that the potential at point B is 0, okay? Far, far away from any charges, the potential at that location is going to be 0. So remember that on the left-hand side of this equation, I have VB minus VA, which is delta V. So VB is going to be 0, and RB is infinity, so that's 1 over infinity, so that term is going to be 0. And then I've got a negative sign on both sides, so those will cancel out. And we can say that the potential at point A, which is just some point outside the conductor, any point outside the conductor, some distance away, is equal to, let's see, Q over 4 pi epsilon naught R A. So if you are some distance on the outside, whatever that distance may be, okay, you can find a value for the potential at that location near some conductor that has a charge Q on it. Of course, if I make RA get big enough, right, if I get very, very far away, this gets larger. As I get farther away, the potential is dropping. So if I get an infinite distance away, then the potential for that point would be 0 as well. Okay? Let's see. I've got more slide on the next place. There are 2 more parts to this that we're going to do really quick. That's the long part. All right? Let's go over to this and say, let's find the value for the potential at the surface of the conductor. So in other words, we're going to say that R is equal to R0. If you go back and look at the diagram, they labeled the radius of the conductor as R0. So we'll just say that R is equal to R0. Don't think about this too hard. We just found the equation. V is 1 over 4 pi epsilon naught Q over, last time it was RA. Well, now I'm just going to let that be R0, which means it's 1 over 4 pi epsilon naught Q over R0. I'm not sure why that was even a problem. Agreed? Don't you wish they were all like that? We're just picking a value for R and plugging it in. And then finally, find V at a point inside the conductor. Any thoughts? It's a quick answer. Not as quick as you might be thinking, but quick. So in other words, we're looking for a place where R is less than R0. Keep in mind that in a conducting material, the electric field is equal to 0. If the electric field is equal to 0, then we can also say that delta V is equal to 0. Delta V is equal to 0. And that's between the surface and any point inside. If the change in potential or the difference in potential between the surface and any point inside is 0, well, that just means that this answer applies everywhere inside. V is equal to 1 over 4 pi epsilon naught Q over R, where R is less than R0. I like parts B and C of this problem because, well, the answers come kind of quickly. Let me label these B, C. I'll go back over here and call this A. take a look at the graphs over on the right. Electric field and potential at different distances from the middle. We can see the graphs of the things we just found. So first of all, notice that the potential decreases as 1 over r as I get farther away. This whole thing is proportional to 1 over r. So the biggest it's ever going to get is when I'm really, really close, right at the surface, and it turns out it has that exact value everywhere inside, and then it falls off proportional to 1 over r as I get farther and farther away. That's what the potential is doing. The electric field, on the other hand, remember our electric field equation is proportional to 1 over r squared. And we saw that right there at the top on this slide, right? 1 over 4 pi epsilon naught q over r squared. So we know as we get farther and farther away from the surface, the electric field is decreasing according to 1 over r squared, but the electric field inside is nothing. So you can see this drops immediately to 0, and everywhere inside the conductor, there's no electric field at all, even though there is a potential at all those points, okay? So we see something here about the relationship between the potential and the electric field. Does anybody have any questions before I ask you a few of these multiple choice questions and then give you a problem to work? I'm going to give you another Gauss's law problem because I've just seen the looks on your face, the love that you have for Gauss's law. Like some of you have already had the word Gauss like tattooed on various limbs, you know, because you're just like, oh, Gauss's law. Just so in love with this whole idea. I understand. I have 6 Gauss's law tattoos. Yeah. No. Okay, next slide. Next slide. I'll give you a second to think about it. What do you think? You have a question?
Yes.
Yes.
So, just to clarify, the potential of a conductor is equal and opposite on the inside as what it is on the surface.
Equal and opposite?
Yeah, so what I'm not understanding is because the overall difference in potential is 0.
This is the difference in potential between this point right at the surface and any point on the inside. So the difference is 0, which means it doesn't change. It's a constant value.
Okay.
Okay? Anybody have any votes here? It says 1, 2, 3, 4, 6. The answer there is 1. If you just think about it as how much opposition you're going to face, if I try to take this positive charge and push it this way, well, that's going to be harder than trying to push it any other direction because I'm going sort of directly upstream, right? It feels a force from the electric field this way, and I'm going to be directly opposing that. So that's going to take the most work from me to try to move it in that direction. But there is a direction where perhaps it is 0 work. I don't know why there's a box over there on the left. That's kind of strange. A strange remnant of something. 1, 2, 3, 4, 5. Think about what happens if I go, first of all, here we determined I'm fighting against the force, against the electric field. That's going to be the most work. If I go this way, well, actually the electric field is helping me. That's going to be like the easiest in some ways. It's like, oh, I'm not really having to do anything. It's like moving itself. Here, I'm kind of going sort of like against, but not fully against the force that's fighting against me. Here, I'm not working against the force at all. I'm going perpendicular to the force. So in that particular case, I'm not doing any work trying to move the charge from point P over to 3, okay? And that is the last of those, which means it's time for me to give you all a problem. Does anybody have any questions about today's stuff before we revisit Gauss's law once more. No? All right, so I'm gonna switch back over here and see if I can get this to add a slide real quick for us. Hello. And I'm gonna give you something that looks familiar but is a little bit different. So let's see, we use red for the actual shape. So let's say we have a circle, we have another circle. Let's say once again that this is like solid material and there's a hole in the middle, and this looks so much like a donut right now I can just hardly stand it. I've drawn a donut. I think it's glazed in little red lines that I'm sure are delicious. I'm going to stop thinking about donuts now. We're going to say this time that this is an insulator. And there is charge sort of scattered all through here. And what else did I want to give you before turning you loose on this? Make sure I get it right. Let's say that there is also a charge in the middle, which will be, we'll call it SQ. And then I'm going to say that the total charge in the insulator is plus 2Q and evenly distributed. So we're going to have a volume charge density which is equal to 2Q over the volume. So this is a spherical insulator. So sadly, not a donut, or is this even better? This is a spherical donut with a hole in the middle, and maybe it's cream filled. I don't know what's happening at this point. A spherical donut. There's a gap in the middle, and then a charge right at the center. Here's what you need to find. Find the electric field in 3 places. And let's label some things here. We're going to call this R1. Once again, we'll call this R2. So we'll say, first of all, part 1 will be for R less than R1. So in that space where there's no material at all, and actually you should already have that answer based on what you did in Tuesday's class. Number 2 is the difficult one, and that is when R is in between R1 and R2. And number 3 is R greater than R2, and that answer you should be able to get to really quickly based on your work in the problem on Tuesday. It's only part 2 that's significantly different. Okay, the other 2 parts should be relatively fast. So take the rest of the time. You've got 21 minutes to try to get to some answers. I will provide a few answers on the screen as you work, but not until you try for a few minutes yourself. So go. I'm going to make one change. Is that okay? It'll actually make it a little easier for you. I'm going to say the total charge in the insulator is just Q, just like the one on the inside, so positive Q, which means that volume density will just be positive Q over V. That'll make your lives a little bit happier. Maybe not a lot happier, but a little bit happier. Ever so slightly happier.